Okay, good afternoon, everyone. Good to see you all, and welcome to our bi-weekly seminar. So today it's my pleasure to introduce Jonathan Gorard. We tried to find out whether that was French or not and how to pronounce it, but Gorard was the accepted, one of the accepted variants anyway. Yeah, Jonathan is in Cambridge, as a researcher at Cambridge, and also associated with the Wolfram project, which he is going to talk about in more detail. So I'm probably not going to say too much about that, except that we've all been hearing about Wolfram and his work on Mathematica 20 years ago, and sort of work on automata and sort of models of computation before that, and sort of this all flows into this Wolfram project, which yeah, Jonathan is better placed to explain than I do. And he's directly involved with that. He's also leading a sub-project, also have several sub-projects in this overall space on partly sort of things like theorem proving and rewriting and so on. And the reason why he's here, as you can see from the title, is that in this project they use graph rewriting specifically, but also category theory in sort of more generally, which we're sort of curious to hear about. So Jonathan, please take it over.
Well, thank you very much, Reiko, for that very kind introduction. And thanks also to Nicholas and Reiko and all of the organizers for, well, for putting together these wonderful GReTA seminars and making us all feel so very welcome in the graph rewriting community, and for making this terrible error of inviting me along to come and speak. I hope only that I have something interesting to say, but no promises. Okay, so today, as Reiko mentioned, I'm going to be talking about some new approaches to doing fast diagrammatic reasoning over general combinatorial structures, and considerations of kind of the compositional and categorical and causal semantics of graph rewriting systems, where these new ideas actually come from a somewhat unlikely source, namely from mathematical physics. And so don't worry, this is not going to be a physics talk. I'm going to focus primarily on the mathematical and compositional and theoretical computer science aspects. But perhaps before I really begin, I'll make a couple of very brief philosophical remarks to kind of give some motivation and explain why we care about these kinds of questions in the context of wanting to do mathematical physics. But before I do that, I should just mention that a lot of the work I'm going to be presenting here today is joint work with Manojnan Namaduri and Xerxes Asawala. Our latest paper on the topic that I'm basically going to be talking about today came out a couple of weeks ago on the archive, and it builds on some previous work that we did, as well as as well as kind of being broadly within the context of this underlying formalism that was developed, as Reiko said, by Stephen Wolfram. Well, the origins of it go back really to 2002, but its kind of modern form was developed sometime last year. So if you want to find out more, please do feel free to go to read any of our stuff. But yes, so this talk will primarily be based on these two papers with myself, Mano, and Xerxes, as well as some earlier work by me. Okay, so first to give a bit of background to why we might care about graph rewriting in the context of doing mathematical physics. So it turns out, rather surprisingly, that a large class of questions in fundamental physics can essentially be reduced to problems of graph rewriting. So to give one example, which I'm going to show here, it turns out that discretizing the Cauchy problem in general relativity, doing sort of numerical simulations of curved spacetimes and things, can essentially be reduced to a graph rewriting problem, because what you can do is you can approximate your a Riemannian manifold. You can approximate some space-like hypersurface as an undirected graph. And then you can define the dynamics that tell you how one space-like hypersurface evolves to the next, just by having graph rewriting rules applied to that graph. And we know we proved this last year, that there exist large classes of these rewrite rules that satisfy the Einstein field equations of general relativity in the continuum limit, because they effectively obey some kind of discrete action principle that converges to the Einstein-Hilbert action in the appropriate limit. So for instance, we can define, as we're doing here, these are three hypergraphs of varying resolution, effectively 200, 400, 800 vertices, corresponding to an initial space-like hypersurface in which we have two black holes on the left and on the right. And if we just evolve this hypergraph rewriting system using a set of rules that we know converge to the Einstein field equations in the continuum limit, we can actually simulate relativistically the merging of these two black holes down to until eventually they ring down and produce a single larger Schwarzschild black hole. So this is a way of doing practical numerical relativity simulations just in terms of graph rewriting. And you can see that we're actually coloring these graphs based on information about the local conformal curvature. And again, that's a whole other story, which I'm not going to talk about here, but suffice it to say, you can infer various features of the continuum geometry just by looking at the combinatorial structure of the graph. So if you have an undirected graph that's approximating some d-dimensional manifold, you can find out that it's approximating a d-dimensional manifold by looking at essentially, looking at a particular vertex and then looking at vertices adjacent to that vertex and vertices adjacent to those vertices and so on, growing out some neighborhood graph of radius r, and then looking at how the number of vertices scales with r. And so obviously, if it's an approximation to a d-dimensional manifold, you expect it to grow like r to the d. If there's curvature, that manifests as a second order correction term from which you can then extrapolate things like the Ricci scalar curvature. Or if you look at growth rates of things like geodesic tubes or geodesic cones, you can infer projections of the Ricci curvature tensor and generally just excavate higher order contractions of the Riemann tensor. So that's effectively what we're doing here. The red parts of this graph correspond to regions of high curvature, blue parts correspond to regions of low curvature, and this is information that we're inferring just from the structure of the graph in a completely coordinate-free manner. And from that, we can then construct essentially a three-dimensional reconstruction of what the space-like hypersurface looks like projected onto a two-dimensional plane. And we can see, again, that the merging of these two black holes simulated as a pure graph rewriting system. Another just quick example of a place where, again, we can reduce these questions from fundamental physics into problems of graph rewriting comes actually from a completely different place, from the foundations of quantum mechanics and quantum information theory. So this idea really has its origins in the work of Samson Abramsky and Bob Kocher in 2004, the development of the categorical quantum mechanics, and later on with the work of Bob Kocher and Ross Duncan in the development of the ZX calculus, or the ZX calculus, depending on which side of the Atlantic you're on, where the basic idea is you can represent any quantum circuit, but actually more generally, any linear transformation between qubits in a finite dimensional Hilbert space as some open labeled graph called a ZX diagram, which you can see here. So this is an example of a ZX diagram. So each one of these vertices is called a generator or a spider. So the green generators correspond to generalizations of rotations about the z-axis on the Bloch sphere. The red spiders correspond to generalizations of rotations around the x-axis of the Bloch sphere. The H generators are sort of Hadamard gates. The black diamonds correspond to scalar factors and so on. So any linear transformation on a finite dimensional Hilbert space can be represented by a labeled open graph of this form, which means we can then do quantum mechanics by just manipulating these graphs. So we can reduce all of the standard rules of finite dimensional quantum mechanics to pure rewriting rules on these labeled open graphs. So here's an example. Here's a subset of the complete enumeration of the rules of quantum mechanics, or specifically the rules of the ZX calculus, represented as pure diagrammatic substitution rules on these labeled open graphs. And it's important to note actually that these rules many of these are not individual rules, they're actually infinite rule schemas, because for many of these things, there's one rewriting rule for every possible configuration of input and output arities for the generators. And although I'm not going to talk about that right away, that will become relevant to some things I'm going to talk about later on. Okay. So then that means we can reduce these questions about, say, which sets of linear transformations are permitted, or which classes of quantum circuits are equivalent to what other classes of quantum circuits, or whether some particular unitary operator on a Hilbert space can be represented without a particular type of gate or whatever. All these general finite dimensional quantum mechanics questions can just be reduced to questions about abstract rewriting systems defined over open graphs. Okay, so these are two examples. We have many, many more. And basically, it turns out, excitingly, that very many problems from relativity, astrophysics, cosmology, quantum mechanics, quantum information theory, quantum field theory, etc., can all be reduced essentially just to graph rewriting problems. And the Wolfram project that Reiko mentioned, in a sense, its general philosophical goal is to reduce all of fundamental physics to a problem of graph rewriting. We haven't succeeded in that yet. We're several steps away, I think, but so far the results look very promising, and it's really a very interesting kind of place of confluence between these two areas. But as I say, I'm not primarily going to talk about physics today. What I am going to talk about is that thinking about this kind of stuff leads to a very, very immediate practical sort of software engineering problem, algorithm design problem, which is that to produce these kinds of visualizations or these kinds of simulations that I'm showing here, we often have to perform, diagrammatic rewriting over combinatorial structures, be they open graphs, hypergraphs, whatever, involving tens of thousands or even hundreds of thousands of vertices, and many times involving tens of thousands or hundreds of thousands of rewrites. And often, obviously that's a very computationally difficult problem. And so, it leads to this obvious question of, does this new approach to thinking about the foundations of physics give us also potentially new efficient ways of doing diagrammatic reasoning over combinatorial structures? And excitingly, the answer seems to be yes. And that's kind of what I want to talk about today. Okay. But so before I get to the interesting stuff, let me begin by telling you all some things that you know perfectly well, probably much better than I do. So I apologize for the slightly elementary nature of my first few slides, but it will help to kind of contextualize the stuff I'll say later on. So we start, at the baseline level, the Wolfram model, you can think of it as just being your ordinary, standard bargain basement, DPO rewriting system. So what we're doing is, we're representing directed graphs, or more precisely directed multigraphs, as functors from some category G to the category of sets, where the category G is just a small category that consists of two objects, E representing the edge set, B representing the vertex set, and a pair of morphisms in the Hom set, S representing the source vertex of a given multi-edge, and T representing the target vertex of a given multi-edge. So then the category graph, which is the category of directed multigraphs, is simply the functor category G set. And the reason we set things up that way is because although this initially seems to be restricted purely to directed multigraphs, actually pretty much any combinatorial structure you could think of can be represented in this exact way just by slightly modifying the category G. So for instance, if we wanted to represent undirected multigraphs, all we have to do is define a forgetful functor that just loses the information about which morphism was S and which morphism was T. Or if we want to represent multi-hypergraphs, as we do in the Wolfram Physics Project, we can do that just by adding additional morphisms to the Hom set. Because we have two morphisms, this is a directed graph. If we wanted to represent an arity n hypergraph, we would have n morphisms between E and V. Okay, so that's the setup. So we end up with directed graphs like the thing on the left here, or directed hypergraphs like the thing on the ordered hypergraphs like the thing on the right. And just as a sort of notational convenience, we represent these as essentially multi-sets of ordered relations between elements. So here we have a multi-set 1, 2, 1, 3, 2, 3, 4, 1 for the directed graph, and the multi-set 1, 2, 3, 3, 4, 5 for the ordered multi-hypergraph on the right. Okay, so once we have that representation, then we can do the ordinary DPO sort of stuff that we're all familiar with. We start with some span of monomorphisms, rho that represents our rule, with an interface graph K that's the common domain, a left-hand side L, right-hand side R, with the rule match then being some morphism from the left-hand side onto G, where that rule is applicable if there exists essentially a push-out complement that is responsible for extracting the left-hand side from G and leaving this invariant subgraph K, and a corresponding push-out square that's responsible for then injecting or gluing in the right-hand side R into this invariant subgraph. And that's the general context of this stuff. And again, as you all know, the category graph is not the only category over which you could do DPO rewriting. Generally, these systems are defined over adhesive categories, which have sufficiently similar properties to the category graph that DPO can be reasonably defined. And the general way you set that up is by considering the Van Kampen square condition. So you say, I've got some span of morphisms, common domain A, I'll call them G and F. And then a Van Kampen square is the push-out square F prime G prime with the morphism of F prime G prime with common codomain, with the property that these two faces of this cubical diagram are both pullbacks, and where the push-outs F prime G prime and those pullback squares satisfy some obvious compatibility conditions, which I won't discuss in detail here. And then an adhesive category, which is the standard setup for DPO, is any category. So I should say this push-out, if this is a span of monomorphisms, we call this push-out a push-out over that or along that monomorphism. So if a category has push-outs along monomorphisms, has these pullback squares, and in which every push-out along a monomorphism satisfies the Van Kampen square condition, we call that thing an adhesive category. And for subtle technical reasons that you probably all know, and I can't be bothered to explain, that's a general setting for defining a DPO system. And again, as you probably know, if you take a slice category or a co-slice category or a functor category of an adhesive category, it will itself be adhesive. But in general, if we define some full subcategory with some arbitrary embedding functor, that subcategory will not generically inherit adhesivity. However, it turns out to be the case that, and this is I'm now using the formalism that was developed, or at least exposited by Alex Kissinger here. We can define these so-called partial adhesive categories as formalized by Kissinger, and that's significant to us because our Wolfram model hypergraphs, although they're not the category of Wolfram model hypergraphs, turns out to be partial adhesive but not full adhesive, and partial adhesive categories are a way of kind of formalizing the idea that your subcategory, though it is not strictly adhesive, can inherit sufficient, quote unquote, sufficient adhesivity for you to be able to define DPO. And so basically, the way that works is really, really simple. You have some subcategory C prime of your category C with some embedding functor, and as long as that embedding functor preserves monomorphisms, then the category is partial adhesive, and you can do DPO. And all that has to be changed in your standard DPO specification is that you have to enforce this constraint that that each one of your diagrams, like your push-out complements, your pullbacks, etc., each one has to be preserved by the action of this embedding functor. So we define, say, an S span as just being a span, a pair of monomorphisms, A to B, A to C, for which there exists this push-out diagram, which we call an S push-out whenever it's preserved by the embedding functor S. So we can define an S push-out complement in exactly the same way. In other words, wherever this complement diagram, this push-out square here, is itself preserved by the embedding functor and is therefore an S push-out. And so then our rewrite rules, our spans of monomorphisms rho have exactly the same form, and our matches M from L to G have exactly the same form. The only additional constraint is that anytime we have if we have a pair of morphisms L and M for which there is an overlapping codomain and domain in the Hom set of the subcategory, then they have a push-out complement for a pair of morphisms with overlapping codomain and domain. So in other words, if we take the push-out complement, this square here should be an S push-out square, should be an S push-out complement. It should be preserved by the embedding functor. And so then the rule is S applicable if we have an ordinary double push-out diagram. We have a push-out complement and a push-out square where both of these sub-diagrams are preserved under the embedding functor. So that's just all we're doing is we're saying, we enforce this constraint that the monomorphisms are preserved by the embedding functor, and we enforce the constraint that all the diagrams are preserved by the embedding functor. And then we can just directly port, the full apparatus of DPO to kind of this much more general setup of partial adhesive categories, which are useful for formalizing lots and lots of kinds of combinatorial structures, not least string diagrams, ZX diagrams, open typed graphs, and crucially, the kinds of combinatorial structures that we consider in the context of the Wolfram model. Okay. So that just means now we can have rewriting rules that look like this. So again, we're just for notational convenience, I'm going to represent these as set substitution systems. So rules that just take subsets that match certain patterns and replace them with subsets matching different patterns. And so then we can apply that to some initial hypergraph like this one here with two self loops in it. And we're applying this with a particular update strategy, and the update strategy that we're using is, so in general, if you're given some hypergraph and you have some rule, then obviously, as you know, that there'll be, there could be many different places where that rule can apply, and crucially, there'll be many non-overlapping sub-hypergraphs where the left-hand side of the rule could match. And if they're non-overlapping, then in a sense, it doesn't matter what order you apply the rules in. So you can consider those rewrites effectively to be simultaneous. And so you can just apply some maximal set of non-overlapping sort of hypergraph transformations. And that's what we call a generational evolution. And that's what we're visualizing here. So we're seeing a generational evolution for this particular set substitution rule. And if you want to see in more detail exactly how that works, how that all pieces together, here, this is showing each individual rewrite in that generational evolution where the hyperedges that are being rewritten are highlighted in red. So you can see that we start with this initial subhypergraph here. Then that gets rewritten in just one place because there's only one place where the rule could be applied. At the next step, step 2, there are 2 places where the rule could be applied. So we have 2 rewrites here. At the next step, there are 3 non-overlapping places where the rule could be applied. So we have 3 rewrites there. For the 4th step, there are 5 places. So we have 5 rewrites and so on. Okay, so that's at the basic level. That's kind of how we think about Wolfram model evolution. But if that were all there was to it, it would be a very, very boring talk. So it turns out that there's actually a lot more structure going on underneath this. So the first and most obvious thing that you've probably all sort of realized already is that this statement that there's some canonical updating order is kind of not really correct, right? Because of course, in general, you don't have just there isn't just one canonical set of non-overlapping, of maximal non-overlapping subhypergraphs to which one applies the left-hand side. In general, there'll be many possible such sets. They are all equally consistent. And in general, different such updating orders will yield non-isomorphic sequences of hypergraphs. So what one has is not a single, a nice path rewrite, but actually some more general abstract rewriting system. Okay. So how do we think about that abstract rewriting system in our context? Well, so obviously at the basic level, you've just got some set of objects, which in our case are hypergraphs A, and we have a binary relation, the rewrite relation arrow R. And for the particular Wolfram model case, actually, this is because we can have multiple rewrite rules as part of a single set substitution system, like you saw with the ZX calculus rules before. That was a single rewriting system, but with a whole infinite parametric family of rules. So what we really have is a binary relation arrow R is an indexed union of subrelations indexed by some index set lambda. And then so our abstract rewriting system is really a labeled state transition system at a lambda arrow, which you can think of as being a bijective map from the set of hypergraphs of A to the power set of the set of hypergraphs indexed by lambda. So we're mapping a hypergraph P to an index alpha and a hypergraph Q. And we can formalize that a bit more by thinking of this as being an F coalgebra for the power set functor, if you want to think about this in more compositional terms, because the reason we can think of it that way is because the power set construction, if you want to do it over the category of sets, the power set is just a covariant endofunctor. So in other words, it's an endofunctor, it maps the category of sets to itself, and it's covariant in the sense that it preserves the direction of composition of morphisms and it preserves the identities. So in other words, therefore, our Wolfram model abstract rewriting system A arrow R is just is a category that consists of a single object, A, the set of hypergraphs, with an additional morphism, the rewrite relation, which is really a morphism of the category set mapping from A to the power set of A. Okay. So far, so boring. And so we can visualize that abstract rewriting structure in a bit more detail if we want to do. This is what we call a multi-way evolution graph. So this is just it's kind of the obvious thing. It's just a directed acyclic graph where each vertex is a single hypergraph state and each edge is a rewrite, and in which the vertices have been merged on the basis of hypergraph isomorphism. So in other words, this gives one a way of effectively parameterizing the set of all possible updating strategies, the set of all possible updating orders. And so then a confluent Wolfram model rewriting system is one in which every sort of bifurcation in this digraph eventually merges. And so then, so as I say, this parameterizes essentially all possible updating strategies. So then a particular updating strategy or a particular updating order corresponds to a particular path. So the canonical updating order that I showed you on the previous slide corresponds to this particular path shown in red here. Okay, like I said, that's all very boring, very standard stuff. Where does this get interesting? Okay, well, it turns out if you stare at this multi-way evolution graph for a bit and you squint, you begin to realize that there's a lot more algebraic structure underneath the surface than there might initially seem to be. So in particular, one of the first things you might notice is that actually these multi-way evolution graphs form what we call monoidal category, or what is called in category theory, monoidal categories. So many of you will probably know what these are, but just to kind of take you through very quickly what the idea is, you have some category and it's equipped with a bifunctor, that is to say a functor from the product category C cross C onto C, that is both associative and unital up to natural isomorphism, by which I mean there exists a natural associator isomorphism alpha, whose components look like this, and left and right uniter isomorphisms lambda and rho for the left and right identity objects, whose components look like that. And so the monoidal structure is then, is the reason why our particular multi-way evolution graphs have a natural monoidal structure is that if you look at one of these things, you quickly realize that there are really two ways you can compose the arrows in this multi-way evolution graph. You can compose them sequentially, as we do along these paths, along, say, the red path here, we've got arrow, sequentially composed arrow, sequentially composed arrow, or you can compose them in parallel, which is what we do in between paths. So, this arrow here and this arrow here are composed in parallel because they correspond to different updating orders, even though eventually those two updating orders converge because that critical pair eventually merges. So, so what we have is we have the ordinary composition of morphisms, and we have this additional monoidal composition of morphisms that corresponds to the fact that we can have multiple paths running in parallel. And so then, as we, I won't take you through the whole argument here, but as we proved, as Mano, Xerxes, and I proved in that first ZX calculus paper, as it turns out, this you can really encode this monoidal structure as a disjoint union of these indexed subrelations. So in effect, what happens is the monoidal structure inherits all the algebraic properties of the disjoint union. So in particular, it's trivially associative. It has left and right it has left and right identity objects, because you can always append the identity. You can always append some identity rule. And it's also commutative, because the disjoint union operation is commutative. Our monoidal structure is also symmetric, which means that there exists a natural isomorphism sigma, the symmetry isomorphism in the Hom set, whose components look like this. Okay, so already we've got a slightly non-trivial algebraic object. Our multi-way evolution graphs are really symmetric monoidal categories. But there's a bunch of other stuff going on here too that you also may not have immediately seen. So another feature of these multi-way evolution graphs is that they are equipped with an involutive structure, with an involutive functor. And the reason is because if you think, again, if we think about these as being generated by a DPO system, so we've got our rewrite rule, which is some span of monomorphisms rho with index graph K, left-hand side L, right-hand side R. So we've got K goes to L, K goes to R. If we swap the objects L and R in some appropriately careful way, that will essentially, then we're inverting the rewrite rules. That will have the effect of essentially inverting all of the evolution arrows in this multi-way evolution graph. So if we take this thing and we invert all the arrows, that's a map from essentially the category onto its dual, or vice versa. And that operation is clearly involutive. So what we get is what is known as a dagger structure. So in other words, so we've got some involutive functor dagger from the dual category C op onto C. That has compatibility with the monoidal structure, by which we, and I'll explain maybe in greater detail later exactly what that means. But essentially, all we're doing is we're saying for every morphism F in the Hom set from A to B, there's some adjoint morphism, a dagger morphism from B to A. And then if we take the dagger of any identity morphism, we get back to the identity morphism. And where the dagger structure reverses the composition reverses the direction of composition. So if I have morphisms F and G with overlapping codomain and domain, then G compose F dagger is F dagger compose G, which goes from C to A. So clearly, this, if we just invert all the directed edges in these multi-way evolution graphs, that's trivially an involutive operation. As was described in great detail in our first ZX calculus paper, that we also get compatibility with the monoidal structure of parallel composition and all these other things. Okay, so that's another sort of algebraic feature of these multi-way evolution graphs. And there's a third and final feature of interesting algebraic feature of these multi-way evolution graphs, which is actually specific to the fact that they are hypergraph systems. So the two properties I mentioned so far are general, that they would apply to a multi-way evolution graph for any abstract rewriting system. But the fact that these are hypergraphs actually introduces a new feature, which is that for any one of these hypergraphs, for any one of these vertices that corresponding to a hypergraph state, we can take its dual. In other words, we can for any hypergraph H with vertex set V and hyperedge set E, we can take the dual hypergraph H star with vertex set V star, hyperedge set E star, where the vertex set of the dual hypergraph is just the edge set of the hyperedge set of the original hypergraph, and where the hyperedge set of the new hypergraph is the set of vertices of incident vertices in the original hypergraph. So that gives us a dual structure. And that dual is trivially involutive. H star star is always isomorphic to H. And so, that induces what, in category theoretic terms, is called a compact structure. And specifically, it means that our category is compact closed. So formally speaking, what we're saying is that for any object in our category, there is a corresponding dual object that is unique up to a unique isomorphism, up to a canonical isomorphism. And so the way we formalize that is by, in terms of a compact structure, we have a morphism E to A, or for every object, we have a morphism E to A, which we describe as the unit morphism, and we have a morphism epsilon A, which we describe as the co-unit morphism that just takes you from the identity onto the dual product with the object, or the object product the dual onto the identity object. And so in the case of our multi-way evolution graphs, all three of these structures are compatible. They all satisfy the obvious compatibility condition. So the monoidal structure, the dagger structure, and the compact structure, by which I mean the unit and co-unit morphisms, are all compatible. Now, from a fundamental physics point of view, that's really, really interesting, because when one is first confronted with these multi-way evolution graphs, when one is confronted with because as I mentioned at the beginning, we're kind of thinking of these hypergraphs in a physics context as representing, states of space-like hypersurfaces. And so when one's confronted with this multi-way evolution graph, one's confronted with the fact that actually there is no unique state of space at any given point of time. There's no unique space-time state. Rather, there is always a collection of possible space-time states. So, here, at level 2 here, there are 3 possible states. At level 3 here, there are a bunch of possible states. I can't be bothered to count them, etc. And immediately, if you're a sort of mathematical physicist, you might think, okay, this sounds a lot like a quantum superposition, right? This sounds a lot like you're saying space-time doesn't have a unique state at any given point. Rather, it only ever exists in some superposition of states. And so the reason we started thinking about the compositional structure of these multi-way evolution graphs was by really trying to make formal that intuition. And the way we did that was by, as I say, realizing effectively that what we had here were dagger compact categories, dagger categories that were compact closed and which had a symmetric monoidal structure. And the reason that that's significant is because the category FD Hilb of finite dimensional Hilbert spaces is exactly a dagger compact closed category. So the idea, the intuition behind that is that, so remember, in our case, our monoidal product is just the parallel composition of evolution edges. In FD Hilb, that's the tensor product of matrices. In FD, whereas the sequential composition of morphisms in FD Hilb is just ordinary matrix multiplication. Then the dagger structure, which for us is the inversion of evolution arrows, in FD Hilb is the standard Hermitian adjoint or conjugate transpose operation on linear operators. And similarly, the compact structure is the standard dual, it just corresponds to the standard notion of a dual vector space. So what that means is that there is immediately a deep formal relationship between our multi-way evolution graphs and the category FD Hilb, and more generally, the setup of categorical quantum mechanics developed by Samson Abramsky and Bob Kocher, because categorical quantum mechanics is all about taking seriously the idea that you can do quantum mechanics in categories that are not FD Hilb, but which have the same dagger compact structure as FD Hilb. And so that means that our multi-way evolution graphs are exactly quantum mechanical objects in the sense of categorical quantum mechanics, and it lets us formalize a bunch of these kind of slightly more hand-wavy notions about slices through the multi-way evolution graph corresponding to quantum superpositions and things like that. But so there's a bunch of interesting physics that goes along with that. But as I say, I'm trying to focus primarily on the purely compositional structure of what we're doing here. Okay, so that's already quite interesting. But actually, in addition to the abstract rewriting structure, the multi-way structure of our formalism, there's a whole other orthogonal direction, which is all about understanding the causal semantics. And actually, okay, sorry, before I discuss that, I forgot I had the visualizations of exactly how that works. So for the ZX,
can I ask a question?
Absolutely.
So I was wondering about your interpretation of what the tensor does. In the example, it looked like you have you use it to compose independent transitions, basically.
Yes.
Okay.
Yes.
But I'm wondering what the action on the hypergraphs is, because traditionally you would think of this as a disjoint union of hypergraphs. But then you only capture the cases of independence where basically the two rewrites are completely disjoint, whereas in general there are cases where they overlap, but they don't change anything in the overlap. And I was trying to understand how that works here.
Right. Okay, that's a really good question. So yes, I mean the fact that, essentially what you're getting at is the fact that we do this merging based on hypergraph isomorphism means that this operation is not very straightforward to define, because you could have the cases exactly as you say, that you have non-overlapping inputs to the rules, which might initially appear to be a problem, but actually because of some accidental hypergraph isomorphism, they turn out to just be a single path. That's a really good point, and actually has to do with that has to do with why we formalize this in terms of a monoidal structure rather than a Cartesian structure. So if we were just, suppose our multi-way evolution graphs did not have some notion of hypergraph isomorphism, so this whole thing was just a pure tree object, then the parallel composition of these morphisms would just be a standard Cartesian product. because in effect, what you're doing, you take some disjoint union of these indexed subrelations, and there's no merging, so you're just essentially taking a Cartesian product of two multi-way systems, and that would all be very boring, and the compositional structure would be less exciting. The fact that we are doing this hypergraph isomorphism means that we are essentially taking this Cartesian product and we're adding in an additional sort of gluing transformation, so that when we product two multi-way systems together, we are not just taking that Cartesian product, but we're taking that Cartesian product with some additional gluing between the hypergraphs. Okay. And that's the reason why we end up with something that is more like a Kronecker product and less like a Cartesian product. And also, which is why we say this is a quantum mechanical object rather than a classical object, because in categorical quantum mechanics, the essential difference between classical physics and quantum mechanics is that in classical physics, everything composes Cartesianly, whereas in quantum mechanics, things compose, as Kronecker products, or more generally as monoidal products. So yes, so the operational hypergraphs is slightly non-trivial to define, because it's essentially it's all at the mercy of this gluing operation that on the basis of hypergraph isomorphism. Okay. That may or may not.
But that's canonical in the sense that you given two hypergraphs, you know which parts to glue, which parts to merge.
Yes, exactly.
So does that mean that the hypergraphs have some kind of interface attached to them that you use for merging, or is that? I mean, yes. Maybe this is too technical now, but would be interested to understand that at some point. How you?
No, sure. I mean, we can discuss it more maybe in the discussion afterwards. But yeah, I mean, just to quickly explain how that works. I mean, the fact that we're treating these as multi-sets of ordered relations means that essentially, yes, when we extract out a particular subset of ordered relations matching some pattern, because we preserve the identities of every element of the relations, with that gives us essentially an index hypergraph when once we extract the left-hand side of the rule, and that indexing lets us do this merging. If every vertex were purely anonymous, this merging operation would probably be impossible, or at least would be extremely difficult. The fact that every vertex is not anonymous means that we can actually we can get away with that. And it doesn't matter from the abstract rewriting point of view, because our rules never act on individual, they never act on explicit hyperedges, they only ever act on patterns of hyperedges.
Yeah, okay, thanks.
Yeah, no, it's a good question. We should discuss more, because there's more stuff to say about that. But actually, I mean, this might help to these pictures here might help to explain a bit more about what I mean by this monoidal product, about this this tensor product operation. Because so if we have two ZX diagrams, so here are two multi-way evolution graphs for a given ZX diagram, but they're obeying different rules of the ZX calculus. So in other words, one is the Z spider identity rules, one is obeying the X spider identity rules. So they are effectively, these are two different indexed subrelations. So if I want to take their tensor product, if I want to take their monoidal product in the multi-way system sense, all I have to do is take the disjoint union of those two indexed subrelations, and I get this monoidal product multi-way system that is, or I get this multi-way system that is effectively a monoidal product of these two initial multi-way systems. And the reason that that's significant is that the reason we spent so long thinking about this translation to the ZX calculus is because in the ZX calculus, there is also a canonical way of taking a monoidal product, which is just to stack two ZX diagrams on top of each other. So here we've taken the monoidal product in the multi-way system way. Here we've taken the monoidal product in the ZX calculus way, as you can see by actually stacking these two ZX diagrams on top of each other. And you end up, and up to state isomorphism, the multi-way evolution graph structure you end up with in these two cases turns out to be isomorphic. And actually, we can drill down in greater detail and produce what we call branchial graphs, which essentially are showing you precisely which of these ZX diagrams, which of these hypergraphs or whatever are being monoidally composed. And so they're effectively showing you things about the common ancestry distance between states in the multi-way evolution graph. So here we have the two initial branchial graphs for these two indexed subrelations. This is the tensor products branchial graph that one obtains by taking the disjoint union of those indexed subrelations. And this is the branchial graph that we would obtain by taking the monoidal product of those two diagrams in the standard ZX calculus. And again, we find that the branchial graphs up to state equivalents are isomorphic for these two cases. And we were able to prove in general that would always be so, that actually our monoidal structure will always be compatible with the standard quantum mechanical monoidal structure that is imposed by the category of ZX diagrams. Okay, so I'm a little bit conscious of time, so I might rush through some of the, there's some technical detail which I might skip because it may not be particularly interesting. But I want to mention that, okay, this is important for kind of the punchline of the talk. In addition to the abstract rewriting structure, there is another completely sort of, or apparently completely orthogonal thing that we can think about, which is the causal structure, the causal semantics. So we can ask, when we have a sequence of rewrites, sometimes those rewrites will depend on each other and the ordering will matter, and sometimes they won't. And in general, the ordering will matter if the input for one rewrite makes use of hyperedges that were produced by the output of a different rewrite. So we can parameterize that by constructing what we call a causal graph, in which each vertex is just a single rewrite, and in which directed edges correspond to causal relationships between those rewrites. And so we have a causal relationship between rewrites A and B if the input for B and the output for A have some non-trivial intersection. So that induces a causal graph. If we take the transitive reduction of that causal graph, we get a Hasse diagram for some causal partial order relation on the set of all rewrites, or on the set of all rewriting events. Well, strictly speaking, it's not actually a partial order relation because by convention, it's not reflexive, but I mean, it's easy to make it reflexive. You just add a self loop to each vertex in the causal graph. But for sort of elegance reasons, we tend not to do that. So it's really just a relation obeying acyclicity and transitivity. So we get these causal graphs that look like this. So here, you can see each of these yellow boxes is a particular rewrite, is a particular event in the evolution of some Wolfram model system. And each of these orange edges is a causal relationship telling one that there is some overlap between the output of one event and the input of another event. And so then if we run that a bit longer, we get eventually some directed acyclic graph like the thing on the right there. Okay. So again, if we want to treat this compositionally, how do we think about this categorical structure? Well, fortunately, again, Bob Cocker, as well as his collaborator Raymond Lal, comes to the rescue, as is so often the case. So Cocker and Lal developed this idea, these concepts of precausal categories and this notion of causal structure via partial monoidal categories. So the idea here is we have this notion of a partial functor, which is a really simple idea. If you have some functor between categories B and C, then with category B being the domain, then the partial functor is a functor from a full subcategory of B, which we call the domain of definition of the partial functor. And then if the domain is a product category, like in the case of the monoidal structure, then this partial functor is called a partial bifunctor. So our causal graphs are equipped with a partial bifunctor structure, a partial monoidal structure. And the reason for that is very simple. It's that just like in the multi-way evolution graph case, our causal relationships can be composed both sequentially and in parallel. But crucially, because this is a partial order relation, because it's a causal structure, only certain collections of these causal edges can be composed monoidally. In other words, causal edges can only be composed monoidally if they're associated with events that are not causally related. In physics terms, we would say that they are space-like separated. If those causal relations are relating events that are causally related, that in physics terms are time-like or light-like separated, then they can't be composed monoidally because the monoidal structure is telling you exactly what the space-like separated sets of events are, what the causally unrelated sets of events are. So we don't have an ordinary monoidal structure. What we have is a partial monoidal structure with only a partial domain of definition. And this satisfies certain necessary conditions that are sort of the obvious extensions of the conditions for a monoidal structure, but to this restricted case of a partial monoidal category. And again, in the interest of time, let me not go in great detail what these mean. But the basic idea is, whenever object A and the identity both exist in the domain of definition, then A partial product I should be equal to A. So as long as both sides of these equations exist, then the structure is unital. And similarly, as long as the two sides of this equation both exist, then this equation is satisfied, which means that the partial monoidal structure is associative, in all the cases where associativity makes any sense. Similarly, partial composition of morphisms is associative whenever it makes any sense, and the symmetry isomorphism of these morphisms is defined whenever it makes sense. Okay, so therefore, what we have here, our causal graphs really are partial monoidal categories that are symmetric strict. In other words, where the associator and the unitar isomorphisms are all identities, and they have to have at least one object, and they have to have a unit object with the property that it is terminal. So in other words, for every object in that category, in our causal category, there is some unique object from that object onto the identity object, and in which the monoidal product exists if and only if these two compositional equations are satisfied. Okay, so we've got these two compositional ways of thinking about what's going on. We've got the dagger compact monoidal structure that comes from the abstract rewriting part of the formalism, and we've got this partial causal monoidal structure that comes from the causal by considering the causal relationships between these rewrites. So we can think about this, we can tie all of this together by considering what we might call the multi-way evolution graph, the multi-way evolution causal graph, I should say, where each blue vertex is a hyperedge, each gray vertex is an evolution rule, or an application of an evolution rule. Each yellow box, each yellow vertex is a rewrite event, and each of these orange edges is a causal relationship between those rewrites. So this multi-way evolution graph is showing you all of the causal relationships between all of the events in this rewriting system, not just on one rewrite sequence, but actually between all possible rewrite sequences. And so again, if we think about this categorically, what we have is some very weird, funky object, or some very weird, funky structure, where we have a category which has two monoidal structures that are just kind of knocking about, right? We've got the dagger compact closed monoidal structure from the ARS side, the quantum mechanical side, and we have the symmetric strict partial monoidal structure from the causal side, from the relativistic side. So as I say, the intuition is that the full, the dagger compact closed monoidal structure is somehow quantum mechanical, and the symmetric strict partial monoidal structure is somehow relativistic. And as I say, the reason for saying that is that we know that the dagger compact closed monoidal structure induces something that's isomorphic to the category FD Hilb, or to the context of categorical quantum mechanics, and this symmetric strict partial monoidal structure essentially induces the conformally invariant structure of a Lorentzian manifold. Because if you take some arbitrary Lorentzian manifold and you look at its conformally invariant structure, it turns out to produce a symmetric strict partial monoidal category of exactly this kind. And this is essentially explaining at a compositional level why the multi-way system limit of our model gives us quantum mechanics, and why the sort of causal graph limit of our model gives us general relativity, as I kind of discussed briefly at the beginning. And there are various different ways you can think about it. So this, as I say, this graded structure where we've got two different monoidal structures knocking around the place is kind of a weird object, and there are a few different ways you can try and formalize it, some of which were actually suggested to us by David Spivak quite recently, like in terms of double categories, or in terms of weak two categories, where effectively what you've got are one morphisms and two morphisms, and in a sense the one morphisms are kind of the monoidal product of the one morphisms is giving us something like the sequential composition, and the monoidal product of the two morphisms is giving us something like the monoidal product. And see that there's a way in terms of these weak two categories that you can formalize this idea that you actually have two different monoidal structures in the same category. And again, from a physics or from a philosophy point of view, this whole structure is very, very interesting, because effectively we can derive certain coherence conditions and certain compatibility conditions between these two monoidal structures. And physically, the way we can interpret them is they are giving us essentially consistency conditions for possible models of quantum gravity, because they're telling us how the quantum mechanical structure and how the causal structure, the relativistic structure, necessarily kind of play with each other. And so I'm not going to go through them here, but suffice it to say, we can derive a whole bunch of of these different coherence conditions, which are important from a purely formal standpoint for understanding the setup of the model, but actually from a physical standpoint are in many ways even more interesting, because they allow us to parameterize different models of quantum gravity in terms of different sets of compatibility conditions between these two monoidal structures. And it lets us do these really awesome things, like we can define functorial transformations from like the category of string theory to the category of loop quantum gravity, and really understand at a deep and formal level that the correspondence between these different different fundamental models for quantum gravity. But anyway, I'm not going to talk about that right now, because this is not a physics talk. Okay, so then, if we wanted to do the same, if we wanted to show this causal semantics for the case of the ZX calculus, it would look something like this. So again, each of these blue vertices is a particular ZX diagram. Each of the yellow vertices is a particular rewrite, a particular application of one of the rules of the ZX calculus. And this is what the multi-way evolution graph structure looks like. Actually, that's not quite true. This is showing a subgraph which is restricted only to a particular class of rules. If we wanted to show the full multi-way evolution causal graph structure for ZX calculus, it looks something more like this, which obviously gets pretty difficult to analyze very quickly. Okay, so that's been an awful lot of setup, but I haven't really got to the point yet. I haven't really got to the punchline of why we care about any of this stuff, right? Why would the wider community, people who care about doing efficient graph rewriting, efficient diagrammatic reasoning, why would they care about this model? Well, it turns out rather remarkably that as well as, category theory, compositional rewriting, etc., being able to inform sort of the physics side of our formalism, actually, it turns out that the converse is also true, that the physical intuition we get from the formalism helps us to think about new ways of doing compositional rewriting. So, as I say, in this recent paper that I put out with Mano and Xerxes a couple of weeks ago, we kind of went through in detail an application of a new graph rewriting, a new efficient graph rewriting technique that's kind of physics inspired, and applying it to this particular problem of the simplification of ZX diagrams. And since I have about 10 minutes left, I just want to take you through in at least a small amount of detail, basically how that works and why I think it's significant to kind of the broader graph rewriting community. Okay, the basic idea is that the causal structure that we get from looking at one of these multi-way evolution causal graphs gives us information that the pure abstract rewriting structure does not give us. And the reason why that's interesting is because what that lets us do is we can take the standard kind of automated theorem proving, automated diagrammatic reasoning methods that come from, standard mathematical logic, like Knuth-Bendix completion or its unfailing variance, and we can essentially extend the standard deductive inference rules that come from those kinds of proof calculi by sort of augmenting them with information about the causal structure that normally a proof calculus would completely omit. So one way we can do that, kind of the simplest way we can think to do that, is we devised a refutation-complete proof calculus for first-order logic with equality for reasoning over these kinds of ZX diagrams or these more general combinatorial structures, where the idea is we take the rules of resolution, of superposition, ordered factoring, and so on, and as defined in standard Knuth-Bendix completion for rewriting calculi. And what we did was, in ordinary equational reasoning, in an ordinary Knuth-Bendix completion procedure, the order relation on the terms, the way that we actually select equations on which to apply these deductive inference rules is we always select the equation that is maximal with respect to the reduction ordering. So in other words, we have a reduction ordering on the terms, and at each point, a given inference rule or a given lemma is formed only ever with respect to the maximal element of that reduction ordering. But given that we have information about the causal structure, we realized that we could actually do a bit better than that. That what we could do is instead define selective resolution, selective superposition, selective ordered resolution, selective paramodulation, etc. Where the idea is instead of ordering these equations, the occurrences of these equations within clauses by the reduction ordering, we order them instead based on their causal edge density. So in other words, what we're doing is when selecting which deductive inference rules to apply, or essentially which lemmas we want to form in our abstract rewriting system, what we do is we look at the paths that are associated with the highest causal edge density. And the intuitive reason for that is that, what is it that you're really trying to do when you're doing automated theorem proving or you're doing diagrammatic reasoning? Well, you're trying to form lemmas, either substitution lemmas or critical pair lemmas or whatever, that shorten, the proofs of future propositions, that shorten the proofs of future lemmas. So you're trying to pick lemmas that have the maximal impact on the shortening of future parts of the proof. And as a first approximation, a good heuristic for that is if you're shown two paths and one of them has a large number of causal edges coming out of it and the other has only a very sparse number of causal edges coming out of it, it's a reasonably good heuristic that the one with a large number of causal edges coming out of it is going to have a more significant impact on the shortening of future proofs, because what it means is that more future rewrites are depending on terms that were produced in the more densely connected path than in the less densely connected path. So what we do is we take take all of our equations, we take all the occurrences of equations within the clauses of our rewrite system, and we order all of them based on the causal edge density of the associated paths. And then we pick which deductive inference rules to apply based on the maximal elements with respect to that causal edge density. And we formalize that by means of the selection function S. And so that gives us a way of doing first order diagrammatic reasoning, which is optimized based on causal structure. Actually, as I mentioned right at the start, the ZX calculus is not really a first order diagrammatic calculus, because the rules, many of them are really rule schemas that apply to all possible sort of combinations of input and output arities for the generators. So what we have to consider is not a first order diagrammatic calculus, but a higher order diagrammatic calculus, a second order calculus. And I'm not going to go through in detail because it's a very, very tedious and elaborate construction. You could, if you like tedious and elaborate constructions, you're very welcome to go and read our paper. But basically what we were able to do was building on the work of Bachmer et al. And the work of Kerber. We were able to define a morphism between the higher order diagrammatic logic L2, which is kind of where the ZX calculus lives, and more general LN for some generic higher order logic, and the first order multi-sorted logic with equality L sort 1, to which we can apply these inference rules for our generalized Knuth-Bendix completion scheme. And that morphism lets us map sets of formulas in the higher order logic to sets of formulas in this first order multi-sorted logic in such a way that there are the obvious consistency conditions, and in which this one is able to show that this morphism is weakly complete and weakly sound, which is kind of all you need in order to be able to do theorem proving, because it means that even if the propositions you end up proving are not strictly logically equivalent to the original propositions you started with, they are still equisatisfiable, which is kind of all that matters. And that's exactly what happens when you try and reduce first order logic to equational logic by means of Skolemization procedures and things like that. Okay, so all of that means that we are now able to do automated diagrammatic reasoning, automated theorem proving over Wolfram model systems, and more generally over arbitrary combinatorial structures in a significantly more efficient way than would conventionally be possible with an ordinary, automated theorem proving calculus, because we are optimizing our lemma choices and our choices of which deductive inference rules to apply based on the causal structure. So, for instance, here's an example of a simple theorem we might want to prove about a Wolfram model system, proving that this particular hypergraph down here can be obtained from this particular initial hypergraph by means of this path. So, if we wanted to do this by conventional, abstract rewriting methods, what we would do is we would just compute critical pair, we would compute the sets of critical pairs of this rewriting system, and we would continue adding critical pairs essentially arbitrarily based on the reduction ordering until we eventually obtained a confluent and terminating rewriting system. And although that would work in most cases, it's not particularly efficient. What we can do instead is we can add only the critical pairs that are going to have the maximal effect on inducing confluence in our rewriting system, and therefore on shortening the proofs of our subsequent propositions. So we obtain a proof graph that looks like this. This is the proof graph for this particular proposition. We're proving that this initial this initial hypergraph here eventually can be reduced to yield this hypergraph here, and we can produce this proof graph without having to enumerate the whole multiway system. And the way you can read this, just for your own interest, is that each of these green sort of arrow-shaped vertices is a particular axiom of our rewrite system. Each of the turquoise diamonds is a hypothesis that we're trying to prove. The red square is the conclusion. Each of the orange circles is a substitution lemma. That's basically an application of a resolution or ordered factoring inference rule. And each of these sort of orange triangles is a critical pair lemma. In other words, that's a place where a generalized completion has been applied. In other words, where we've applied one of our selective paramodulation or selective superposition inference rules based on the causal structure. So we obtain a proof graph that looks like this. And we could do this for a slightly more complicated Wolfram model theorem, like this one here, with a slightly more branchy multi-way system. This is one where actually an automated theorem proving algorithm would take a long time to force these critical pairs to converge, because this is a system that's much further away from being confluent. But again, very, very quickly we can produce an automated diagrammatic deduction and an automated proof graph for that particular equational proposition, showing that this hypergraph can eventually be reduced to yield this hypergraph here. Okay, so but in this particular paper, as I say, we particularly wanted to show that this approach to doing diagrammatic reasoning was at least as efficient, and in some cases more efficient, than pre-existing approaches. In other words, for instance, that we could use these approaches in order to be able to apply there's obviously with DPO, there's this very general hard problem of how do you actually select which pushouts to apply, which rewrites to apply. It's very computationally expensive to work that out, and people often introduce all these kinds of rooted tree type optimizations to get around that issue. So if we could show that this approach gave one a more efficient way of actually selecting which pushouts to apply, which rewriting sequences to follow, then this would of course be a pretty big win. So as our initial kind of application area, because we were interested in actually doing this for using this for practical physics, we considered the case of automated circuit simplification in quantum information theory by considering automated theorem proving over the ZX calculus. So here's an example of a simple theorem in the ZX calculus that's proving correctness of a quantum teleportation protocol. So here's a ZX diagram here specifying a quantum teleportation protocol. The 5 vertices on the left here corresponding to one of our participants, Alice, constructing a Bell basis measurement and enacting it, and the 2 vertices on the right corresponding to another participant, Bob, essentially making a measurement that is classically correlated with Alice's, including some Pauli errors, and then we want to reduce this diagram to a single wire, a single communication channel between Alice and Bob, which is a statement of correctness of this quantum teleportation protocol, and that's a theorem in quantum mechanics and quantum information theory, which we can now prove in this completely automated diagrammatic fashion using this theorem proving framework. And the place where this gets really exciting is if we compare this against existing graph rewriting approaches for doing these kinds of circuit simplification problems. So we compared particularly against PYSICS, which is a framework developed by Alex Kissinger and John van der Wettering, I think, that's specifically optimized for doing these kinds of circuit simplifications in the ZX calculus. And also we compared it against Quantomatic, which is a much more general diagrammatic reasoning framework, I think also partially developed by Kissinger and van der Wettering, but now maintained largely by Hector Miller-Bakewell. So we compared it against both PYSICS and Quantomatic, looking at various kinds of circuit simplification operations, like simplification, reduction of Clifford circuits to pseudo-normal form, or reduction of non-Clifford circuits by reducing the number of phase gates, the number of T gates, applying this to randomly generated quantum circuits with many thousands of gates. And what we found was that, in fact, our automated theorem proving approach, our automated diagrammatic reduction approach, seems to combine both the efficiency of PYSICS, our theorem prover sort of met or exceeded the performance of PYSICS on all of the sort of on all the comparable tests we were able to perform, but it manages to combine that with the generality of Quantomatic, because everything that we've done here can be extended well beyond the ZX calculus to any arbitrary string diagram or any arbitrary combinatorial structure without any loss of efficiency. So this is showing the time complexity of those reductions. This is showing the proof complexity of those reductions, both with and without the causal optimization procedure. And you can see here that actually by optimizing our choice of deductive inference rules based on causal edge density, we achieve a massive, actually in this case, it seems to be a roughly quadratic decrease in both the time complexity and the proof complexity of this automated proof generation. So reducing the average number of proof steps at the top end from something like 4 million proof steps here to something like 60,000, or reducing the time complexity from about 5 seconds to about 2 seconds. And for this much more computationally expensive problem of reducing the number of T gates in these non-Clifford circuits, again, we see roughly quadratic reduction in the time complexity as a consequence of doing our deductive inference rule selection based on the causal structure. Likewise with the proof complexity. So this, I think, is really quite exciting. It means that, I mean, there's a lot more still to be done. There's a lot of new kinds of problems, new kinds of graph simplification issues that we'd like to try and apply this new formalism and this new framework to see whether whether this new approach really is both more general and more efficient than kind of existing DPO approaches, because we make use of the causal structure in a way that no other approach really does. But this, at least for the particular examples that we've tried in this narrow domain of diagrammatic quantum information theory, the results do seem to be extremely promising. And so I think I'm currently over time, so I'll just wrap up by saying that in addition to the papers I sort of flashed up at the beginning, all of the code that's necessary to reproduce any of the simulations or any of the visualizations that I've shown in this talk, it's all free, open source. You can download it from the Wolfram function repository. You can make your own quantum circuits with make-ZX diagram. You can prove equivalence theorems between arbitrary hypergraphs subject to arbitrary set substitution rules using this find Wolfram model proof function. You can evolve any of these arbitrary diagrammatic rewriting systems over combinatorial structures using multi-way operator system. You can extract information about that causal structure, convert them to monoidal categories, all that lovely stuff. It's all that code is all freely available. Feel free to use it for whatever you like. So yeah, let me not speak for any longer. I want to save some time for discussion. So thanks.
Okay, thank you very much, Jonathan, and yeah, very nice talk. Thanks for that. I have a couple of questions. Maybe I start with that and then let people on the chat contribute some questions as well. So I had a kind of general question about the sort of the underlying approach, the philosophy here, because I think you showed two examples that were quite different from each other. So the relativistic example you showed at the beginning, to my impression anyway, that was based on simulation. So you basically have rules that describe how these things evolve, and then you simulate them, and if you do that long enough, you get these nice graphs and show basically how sort of a trajectory over time of an evolution of a dynamical system, essentially, that you discretize using graphs and rules. But on the ZX example, what you showed was quite different, because there you basically use rules for symbolic reasoning, as far as I understand, using graphs rather than terms, because the structures that you're dealing with lend themselves more to a formalization by graphs rather than by terms. And I don't see if there's necessarily a connection between the two. So are these just two levels at which you apply the same technology, or are they? So what is the relation between these two types of examples, let's say?
That's a really good question and a very good point to bring up. So yes, at the surface level, it would indeed appear that these are sort of two different levels to which we're applying the rules. That you know, at some level, I mean, if you wanted to think about it in compositional terms, the relativistic case would be a kind of one category case, whereas the ZX calculus is more like a two category case. But actually, it turns out that distinction doesn't need to be made. And the reason is because one of the fundamental ideas behind these kinds of diagrammatic reasoning approaches, like the ZX calculus, is that I guess it's very okay. I think it's actually very directly analogous to combinators in theoretical CS. So, you know, one of the ideas behind combinators, of course, is that you don't have to make a distinction between the sort of the specification of a computation and the specification of its intermediate state of computation. So in other words, you know, there's no difference between the program and the state and the intermediate state of computation. The combinator expression is the whole thing, and the rewriting rules that you apply to those, the reduction rules you apply to the combinator expression are both, you know, reasoning rules about combinator programs and also rules for actually how to enact a computation in combinatorial calculus. The ZX, I haven't really seen it described in these terms, but our way of thinking about what the ZX calculus really represents is like the analog of combinators, but for quantum mechanics. So a ZX diagram is both a specification of a quantum circuit, but also, and therefore it's, you know, the ZX calculus rules are telling you which quantum circuits are equivalent to which other ones, etc. But also the actual enactment of quantum mechanics on that system can also be described in terms of ZX calculus rules. And so just like with combinators, in a sense that you no longer need to make a separation between those two cases. But yes, it's a very good point. That's a philosophical subtlety that I kind of skated over.
But that applies to the ZX, but on the relativistic side, that was a straight simulation. So there wasn't anything symbolic there, or was there something there as well that sort of spans two levels?
Right, exactly. There's nothing symbolic there, and okay. You know, the ultimate objective, of course, is to get to the point where all of these different approaches can be described in the same diagrammatic reasoning approach, where either we find a purely anonymous symbolic way of doing something like ZX calculus, which means that we can now do, you know, quantum information theory in the same context as relativity, or we find essentially a diagrammatic reasoning language for relativity, which is then compatible with the ZX diagrams. We're currently working on approaches to doing that, like having essentially ZX diagrams that are somehow spatially extended, and where there's compatibility between kind of spatial vertices and ZX generator vertices. But that's still quite speculative, and we don't quite know how that's going to. I mean, if we manage to crack that, that would be a big deal, but that's still quite speculative and in its early stages.
Okay, thanks. Fabrizio had a question. Do you want to unmute yourself, Fabrizio?
Yeah, thanks. So first of all, great talk. I have an observation and a question. The observation is that I bet that if you train some, machine learning algorithm to pick the rewriting rules for you, you will get to something very close to what you formalized here, because I think that basically what you really axiomatize is common sense, is saying, I want to select the lemmas that I will presumably use the most in my reduction. So I'm pretty sure that if you try the machine learning path, you will end up approximating the same strategy. And the question is, you basically showed that you have this category of hypergraphs and rewriting rules, and I mean, it's dagger compact closed, so yeah, you can do quantum mechanics on it. But I would be interested in understanding if you have a reason to believe that the quantum mechanics you do in it is physical. So what I mean is that you are representing a physical system as a graph, and then you are applying the ZX calculus in it, like you showed the example with the black hole, for instance. But obviously nothing assures you in principle that the rules of ZX calculus in that category will indeed model what quantum mechanics, how quantum mechanics acts on that system physically. So I guess that's what you are going towards, but I would be interested in knowing if you have more to say about that.
Yes, I know, it's an excellent question. And yeah, I mean, thanks for the comment. I mean, it would be interesting to work out, just on the comment suggestion, it would be interesting to know, for us, it's, extrapolating details about the causal structure based on the abstract rewriting structure is extremely difficult. It would be interesting to know whether an ML approach could actually succeed in doing that with any kind of, reasonable accuracy. My intuition would be that it might be able to, but I don't know enough about ML to really say with any confidence, but I like that. That's a good idea. Okay, so as for your second question about physicality of quantum mechanics, yeah, I mean, the short answer is we have no idea. We're hoping it turns out to be physical, but we don't know. Right now we're still at the kind of mathematical structures phase. This relates to the question that Reiko was asking in a way, because I think the first indication that we'll have that what we're doing is or is not actual physical quantum mechanics is when we start to have the situation where we're doing essentially ZX diagram manipulation, but in something like a curved space-time background. So for instance, the first problem that I really want to try to solve there is there's strong reason to believe from quantum gravity that as a consequence of Hawking radiation, if you try to enact a teleportation protocol in a Schwarzschild geometry, there's a loss of quantum fidelity, just because of the radiative effect. Yeah. And so if we did that diagrammatic reduction that I showed, and we have ways of extracting the fidelity information from these diagrams, obviously. So if we did that diagrammatic reduction, as I showed on the towards the end, but now embedded in some Schwarzschild, in some hypergraph representing a Schwarzschild geometry, where there was some compatibility condition between the ZX vertices and the hypergraph vertices in a way that we don't fully understand yet, and we saw that loss of fidelity, that would be an initial indication that what we're doing might actually be sensible as physics rather than just categorical quantum mechanics.
Yeah, I mean, but if it ends up being physical, it's really like a galaxy brain kind of moment. That would really be great. Yes.
Right. But yes, no, I agree. It would be awesome. But yeah, I mean, the basic problem is understanding, understanding what the sensible rules for a spatially extended ZX calculus would look like is not straight. I mean, what ZX calculus looks like when you've got, say, a finite speed of light that limits information propagation between generators and things. Understanding how you make all that work with relativistic invariance, et cetera, is not immediately straightforward. But yeah, it's a problem we're working on, and I agree. If it ends up actually producing sensible answers, it'll be a pretty big deal.
Yeah. Thank you very much.
No, it's a great question.
So maybe I could also ask a question, maybe a little bit from the graph rewriting community, maybe, because I happen to be also a mathematical physicist, but by training. But so in the very beginning, you had a moment where you, of course, introduced double-pushout writing, and then pretty quickly moved away from, because in double-pushout writing, there's sort of a canon of standard results. For example, this concurrency theorem and structures like that. And I was just wondering, so because I mean, I wouldn't have been entirely surprised if at some point in your reasoning about these possible monoidal structures or composition structures, you would have seen some occurrence of the concurrency theorem. And simply for the reason that, I mean, the concurrency theorem essentially says something about sequences of 2 rewrite steps, which can then be analyzed by essentially looking at precisely how the rules interact. So, I mean, of course, one of the possible ways is they don't interact at all. That would be a parallel composition. But then there's sort of all of the other options where essentially 2 steps influence each other in such a way that then, in particular, a third step could actually rely on precisely the first 2 steps. So, I mean, sort of associativity, there is this version of associativity in composition, which exactly relies on that you can list all of these options based on recursive application of concurrency theorem. So have you seen any indication? Because, I mean, these parallel compositions are pretty standard in quantum mechanics, I would imagine. But have you ever seen any indication in your work that there should be use for this concurrency theorem?
Yes, I mean, it's definitely something I want to try and understand better, and it may be something I end up pestering you with questions about. Yeah, I mean, so as far as I know, there hasn't been tremendous work on applications of, well, any of like the parallelism theorem or the concurrency theorem or any of these things to categorical quantum mechanics in particular. But I think that's really an oversight rather than being by design.
I mean, just to say that, for example, the commutation relation in quantum mechanics. So, I mean, you can formalize actually the simplest possible quantum mechanical model. So, if you just get sort of the generator and relations picture and really like in quantum mechanics, then actually the commutation relation is precisely a statement about all possible ways you can first create a vertex and then delete, minus the other way. And that minus makes sense because you basically lift all possibilities to vector space structures and then sort of linear operators for each rule. And then precisely by applying the concurrency theorem, you can produce a proof that there is this commutation relation. So a dagger gives you the identity. So, I mean, I would be extremely surprised if this didn't play a role near formalism, but
I completely agree. I mean, we have a very straightforward way of specifying, commutation and anti-commutation of operators just based on essentially critical pair, essentially convergence conditions on critical pairs and so on in the associated multi-way evolution graph. As I understand it, if we attempted to formalize that in terms of a triple push-out condition, then we may have a way of making an actual tangible connection to the concurrency theorem.
So it's much simpler than that. It's just that actually the critical pairs, you can use them also to compose rules, because as you said, like you have a forward, you have this dagger structure, you can revert rules. So basically a critical pair is nothing but a possible overlap of a rule with sort of the reverse of the other. So in that sense, if you find, of course, critical pairs, you can in this case prove that there's exactly the one critical pair where you create a vertex and then delete it. That's exactly the only one critical pair in this simple case. And so, I mean, presumably it's similar to saying in your multiway picture that a sequence of 2 steps is sort of also possible in the other order, producing the same outcome. So, but the basic question is, I guess, about doing combinatorics on the possible sequences of composition. That's where the concurrency theorem comes in. So if there's any such computation in your framework, that would be interesting to look at, I think.
Right. No, I agree. I mean, this is currently an ill-understood thing from our perspective. And so yeah, I mean, if you have, I mean, particularly given that you seem to have done an awful lot of work on the understanding the combinatorics of how large sequences, how path sequences of things of rewrites work. If you have additional insights about that, I mean, for instance, like trying to understand, say, how we can prove a local Church-Rosser theorem or something
exactly.
For a large class of these things. That's something I've been interested in for a while, but we haven't really made any progress on because we've been distracted with other things. But yeah, I mean, if you have insights about that, it would be really interesting.
Excellent. Yeah. Let's have a discussion on this.
Yeah, definitely.
Thanks.
No, thanks for the question.
Thanks.
Do you see connections with the homotopy type theory?
Oh my gosh. Okay, you've opened a big can of worms. That yes, we see awesome connections with well, okay, actually, let me. Okay, so the loose story. This is a whole other orthogonal direction that Xerxes and I have been working on, and which we are about to put out a paper about, but which unfortunately it's not out yet. But yes, so essentially, our multi-way evolution graphs are, as you probably suspect already, are naturally homotopical objects, because essentially anytime we perform a critical pair completion, what we are essentially doing is defining a homotopy between a pair of paths, in some associated space. And that gives us a natural way of constructing higher inductive types. And we can show that in a class of cases, the limit, which is our sort of what we somewhat jokingly call the rulal multiway system, which is just a multiway evolution graph where all possible rules of a particular signature are instantiated. That's the natural limit point as you take, as you start to apply infinitely many of these higher homotopies between these paths. And we can show, again, at least in a class of cases, that rulal multiway system has the structure of a weak infinity one category. In other words, it actually is an infinity. It's at least a shadow of an infinity groupoid in the Grothendiekian sense, which would explain. I mean, the reason we were pursuing that again from a physics standpoint was that it would start to explain at a more foundational level why continuous spatial structures like spacetimes, like Riemannian manifolds, like Hilbert spaces, etc., emerge from this discrete model, because essentially what they're doing, each one of these objects can be obtained by a section of this rulal multiway system, taking a section of this weak infinity one category, and all of the sections then inherit the structure of a topological space via sort of Grothendieck's hypothesis. But actually, since you asked that, I considered briefly talking about this, but I thought I wouldn't because of time constraints. But since you asked, I will just quickly show some a thing that we're currently working on that might be of interest. So these diagrammatic reasoning languages like ZX calculus, when you start to think about them in more detail, there's an idea we had, which is that the proof graphs I showed during my slide presentation, those are also essentially open typed directed graphs, right? And there's no reason why one couldn't define a diagrammatic reasoning language on the proof graphs themselves. So what one can do is, let me show you an explicit example of that just quickly. Sorry, I'm going to share my entire screen for a moment, but this is, okay, so we have a proof graph like this, and then what we can do is we can say, so we've got substitution lemmas, critical pair lemmas, axioms, hypotheses, etc. And then there are certain rules for how these things can combine. So if we have two substitution lemmas and they're adjacent, so then we can actually combine them together and add together their dependencies. And the reason we can do that is because if you've got a substitution lemma going from A to B, and you've got another substitution lemma going from B to C, and they're adjacent, we can merge them together into a single substitution lemma going from A to C. And we can do the same thing in reverse by essentially applying Genson's cut elimination lemma. Similarly, for substitution lemmas with higher arities, there are similar rules. Or if we have critical pair lemmas, then if you've got a critical pair lemma which is adjacent to two substitution lemmas, you can merge them together into a single critical pair lemma and add the dependencies. Again, because effectively, if you've got a critical pair A, B, and A can be rewritten to yield C and B can be rewritten to yield D, then you can replace that with a single critical pair B, D. And likewise, we can do the time reversed version. So I worked out a few months ago that there is a complete and consistent and sound diagrammatic reasoning calculus for mathematical proofs for these proof graphs in the same spirit as the ZX calculus, so you give it a proof graph and it tells you the set of all possible equivalent proofs. It gives you an embedding space for all possible equivalent proofs. So then what we can do is we can take an individual multiway system, we can take a path in that multiway system, convert it to a proof graph like I showed in the talk, then evolve another higher order multiway system which shows the set of all possible equivalent proofs to that original proof, and then construct proof graphs of that, and so on. And that gives us actually a systematic way of constructing higher inductive types whose limit, as I say, in at least a class of cases, we can show is this weak infinity one category. And so this gives us a kind of a diagrammatic pictorial way of doing homotopy type theory via graph rewriting, which I wasn't planning to talk about yet because it's not quite ready for prime time. But this is hopefully a coming attraction over the next couple of months. But it's a really good question.
Thank you. It's beautiful. Thank you very much. Another quick questions. Does this relate at all to Grothendieck topos through the sieves and exploring the space of possible through the sieves topology?
Yes, no, definitely. But we don't know. Okay, what we get is definitely an infinity topos. We don't know whether it is exactly the Grothendieck topos. We don't know in detail how the Grothendieck topology is actually induced. We have reason to suspect it's the Grothendieck topos because, well, essentially from physical intuition. Because if this is actually a model for physics, and physics seems to be well described by topological spaces, it would kind of be too beautiful if it weren't because they were inheriting the topological structure from some Grothendieck topology. But we haven't actually proved that formally yet. But yeah, it's a good point. We have reason to believe that that's a related related concept. Fabrizio, I see, is commenting that we're down the Urs-Schreiber rabbit hole. Yes, this is
definitely, yeah.
We've both Urs and Mike Schulman have been responsible for us spending an awful lot of time thinking about synthetic geometry and other, and how we can make those ideas more kind of directly diagrammatic, which is kind of what we're all about.
I'm definitely not surprised that they are the culprits of this madness.
Okay, so can I suggest that we close the official session here?
Just one question, please. Yes.
Okay,
thank you very much for this talk. I have just one short question. Is about can you use your framework to make path optimization to link with the optimization theory? Thank you.
Yes, again, we think so, but this is not an area that I personally know well enough to be able to talk with any confidence. But yes, path optimization is one area. Okay, a few areas where we think this has immediate practical application: path optimization, sort of multi-agent planning, temporal planning, those kinds of things where, again, essentially you're doing sort of reasoning over classes of multi-way paths. Another class of areas that actually Nick and I were just talking about before the stream is distributed computing, an area which I'm completely clueless about. But again, we have reason to believe that there's, people have made a certain amount of progress. People like David Spivak and so on have made a certain amount of progress in applying these kinds of diagrammatic and compositional ideas to understanding, distributed database systems and so on. And so again, we have reason to believe that there's useful stuff to be understood there with, like, okay, for instance, inducing eventual consistency in a database system, at least at a formal level, seems to be remarkably close to inducing confluence in an abstract rewriting system. And seeing as though we now have a very efficient way of inducing confluence, it's highly likely that will also give us an efficient way of inducing, eventual consistency in distributed databases. These are, it's a great question. I'm far too ignorant to be able to give you an actual answer. But these are
just
all
an idea to pursue your work. And in the same way, level, if we can you consider pattern recognition with your tools between two separate?
So what exactly do you mean? What do you mean by pattern recognition precisely?
If you take two, I will say two systems, and you don't know anything about the two systems, but you do all the graph rewriting.
I see. Okay, so you're assessing some kind of similarity metric between two systems based on graph rewriting distance. Yeah, that's an interesting. I mean, because absolutely. If it's possible to formalize those kinds of problems as essentially, I'm given two graphs, and can I reduce both of them to some common object? Yeah, that's exactly the kind of problem this framework should be well equipped to solve, because effectively it's the same as the automated theorem proving problem, except in that case, you're not necessarily reducing to a normal form. You're just reducing to some kind of intermediate, intersection object.
Okay.
That's a good idea.
Okay. Thank you. Bye.
Okay. So thank you very much, everyone, and Jonathan, for the nice talk. And yes, so I suggest we leave the official channel here, the disconnect from the YouTube channel. But everyone who wants to stick around is sort of free to ask more personal questions in private. Okay.
So thanks again also to Jonathan from my side. And I'll just stop the YouTube channel just to avoid any misunderstandings. So Zoom will stay open. Just stay here for a second. I just have to stop the YouTube. So thanks again to everyone who listened on YouTube. Thanks again to Jonathan for a fantastic talk. And everyone who wants to stay, please stay on the YouTube or join us on the YouTube. The link is put on the YouTube.
Anyway.